Yeah, please, whenever.
Okay. So, thank you, everyone. And in particular, I would like to thank to Professor Lin for his invitation. Today I will talk about the bimodality in the class of self-regulated gene network with a nonlinear promoter transition and faster dimerization. So I would like to emphasize the nonlinear because in the study of bimodality, most of study are based on the numerical computation, and somehow numerical computation is good, but it may not be gain very deep insight from the computer study. So we prefer to have a analytical study. And the most of study in this gene network are based on the numerical computation, or they based on the assumption that the reaction rate are linear. The reaction rate are linear, the fact that the reaction rate are linear allow the people to maybe to derive the exact form of the state distribution. So in this seminar, I would like to say that we develop uh, a framework to analytically study the state distribution with the nonlinear transition rate. So okay, let's do this. Okay. This is the level I would like to study. It's a very basic a building block for the gene network. So we have a DNA in the off state or in the inactive state, and the DNA in the on state or in the active state. And you know the DNA can translate to the transcript to the RNA, and the RNA can translate to the protein. And somehow the two protein can bind together to form a dimer protein. And this process is known as a dimerization process. And in principle, this this reaction are linear, and also the transcription process, the translation process are known to follow the linear rate. However, this part, the dimerization process, because it's a biochem, it's a two molecule, two protein to form a dimer protein. So it's a nonlinear. This rate is not a linear, it's a nonlinear because there are two protein involved in the reaction. In not good. It's this one. This one. Oh, sorry. So this some sample pace at the state state for the network using the Gillespie algorithm. So depend on the parameter we use, we can have a four type state distribution. This type, for example, motor decreasing distribution, and this type correspond to a bimodal distribution, and this type C and type B and type A correspond to the unimodal state distribution. So and you may observe another in this case of type D, the green line show the gene activity, and the blue line show the pace of the number of protein number of protein. So if the gene activity, if you have a very less very few gene activity, then this DNA will not will be always in the inactive state. So so there are a very few protein is translated. So you can expect that this should be a type a Morton decreasing state distribution. On the other hand, in the case of type A, at the very bottom of the panel, if gene activity if is very often the gene is very often close and open, and you can see that there are many the protein. You can see the many protein are produced. Once the gene is in the on state, then some protein should be translated. And because the gene is always is switching the very open between the closed and open, so you can expect that it's a unimodal distribution. So if you would like to have a bimodal distribution, you should be very careful to choose the parameter. The parameter should be in some sense in some moderate range to have such a bimodal distribution. There are many work in this direction, and I can say I list some of them, but not all of them because there are too many data study along this direction. And most of them, as I said in the beginning, they are based on the numerical computation. And for the to my knowledge, there are very few analytical study for the bimodality in the gene network, and I list three. And the first one is very famous paper published in the PNAS in the 2008, and they study a very basic three-stage model. Basically, this model is this one without this dimerization process. Only this the DNA switch the only in this three stage consider the switch between the DNA on and off state, and the transcription process and the translation process. It's a basic three-stage model without this dimerization process. And because because all the Asian are linear, so they can derive the exact solution or exact closed form of the state distribution. But even they can derive this exact form of the state distribution, it's still very difficult to understand or to have the whole picture, which parameter will corresponding to the bimodality, which is a parameter will correspond to the unimodal distribution, or the Morton decreasing distribution, because this exact form of state distribution, this form it's exact, but it's a very ugly, very difficult to analytically to say their property. And in the second work by Je-Chiang and Tsing, they are very nice, but they discuss only the two-state model, so they skip the transcription process, and only a two-state or two-stage model, and they can they use the they can because it's more simple than the three-stage model. So you can expect another they derive the exact from the state distribution, but they use some very clever technique and to divide the whole picture or whole picture for this state picture. I mean that they can have a bifurcation diagram for which you can see now which parameter corresponding to the state bimodality distribution, or which parameter will corresponding to the unimodal distribution or Morton inversion distribution. Anyway, and these two work are based focus on this very basic model. And the Osmo, they in this work they consider this enzyme very basic the enzyme reaction network, and using this the very specific structure of this network, and also use the Feinberg theory, and basically they assume that their reaction rate follow this mass action law. They can have not exact almost not exact but a very good approximate the analytical solution for this enzyme reaction network. So my goal is to develop a framework to analytical study the bimodality without the need of the exact form of state distribution. So I follow the basically in my approach it's my first step towards solution. So I skip the transcription process. I have only consider the switch between the DNA off and on, and the translation process, and also the dimerization process. So it's this linear, but this part, this dimerization again, it's a bimolecule process. So it's a nonlinear transition, either nonlinear reaction rate. This one, and I assume that the dimmer interact with the DNA and through this interaction, and the interaction rate GOD take this linear form. This one, the linear form is one, and linear one. So this dimmer can enhance the when we push the DNA to be in an on state or in an active state. So the more dimmer protein, the DNA is more likely to be in the active state. Okay, and then at the first step, I assume that this fast-dimerization. I mean that the fast-dimerization process means that this process take in these associated process are very quickly and in the equilibrium. So I mean that these the two reaction parameter or constant are very large, but their ratio is fixed. So use this assumption analytically, you can show that this if you focus on the state distribution, then this network will be reduced to this very typical two-state model. So what's the difference between this and this? So because I assume that the dimerization process is very fast, so they are very quickly in the state in the equilibrium. So I can skip this one, and then become this one. But this interaction between the dimer and the DNA, this process, this reaction is included in the reflector in this reaction rate. So the difference again, the difference we can skip this one under the fast dimerization process assumption. But this reaction rate, this one, this linear should be replaced by another nonlinear function. This one, Je-Chiang. And I will talk about this reaction rate later. But anyway, so based on the fast dimerization process assumption, I can reduce this model to this simple two-state model. This one, but again, this linear, but this G-N is a nonlinear. So we still have a nonlinear model. This one. So so I write down the governing equation for this model. So if I say that if we let this is the probability is the probability for we have a total number of protein at the end, and this means that the protein is at the off state or in active state, and this probability means that the total number of protein is small n, and the DNA is unstable. This one. Then this chemical master equation for this model look like this one. But because the protein number can be varied from 0 to infinity, so this is another two-component model. Actually, it's an infinity because this is small n is the number of protein can be from 0 to infinity. So you have infinity number of equations. So if we are infinite number of equations, it's difficult to analytically study this model. Okay. So I say an assumption about this one. This our the activation function. This one. So this G hat is include the effect of a dimerization protein. So the effect of dimerization process is included in this activation function G hat this one. And this activation function is very complicated. It looks like the form of this activation function G hat take this form. So it's a constant. It's a constant, and the Q is also constant. But this function Cn or Q is in this form, and take this and then you see now this is also related to the group of the permutation group. So basically, this function is complicated, and actually it's a nonlinear. It's a nonlinear. But fortunately, this we don't need, because we don't need the exact form. We don't need the exact form of this activation function, and we only use this asymptotic property. So this group here, they in 2009 they showed that this activation function can be shown to have this a nice property. So even this form is very complicated. It's very complicated, but they can show that this activation will actually have this asymptotic property. So G0 is a basal activation rate. Is a basal activation. So without the dimerization, without the dimer protein, you should have some activation rate. This rate is basically is a reflected in this quantity G naught, this one. And this I should say that this small n have no relation with have no relation to the number of protein. It just it's just a sequence. And this quantity is in between 0 and 1. And then if n go to infinity, is go to the 0. It's a positive, and between 0 and 1, and go to 0 if n go to infinity. We only need this property to derive analytical derive some useful result. So I think we know the definition of a static distribution. So basically, this static distribution is mean that it's a solution of chemical mathematical equation, but it's independent of time and satisfy this chemical mathematical equation. So this static distribution is a sequence, and for each n is corresponding to the protein number. So this is the probability for the protein number to be equal to n, and the DNA is in the off state, and this one is corresponding to the protein number equal to n, and the DNA is in the on state, this one. And then also this is this second definition give this magnitude of the probability of finding the n protein, this one. So here is our result. So if you have would like to have a bimodal distribution or multimodal static distribution, this parameter should satisfy this inequality. I will give some biological implication for this inequality later. So this is a necessary condition, this one. And we have also a sufficient condition. For the sufficient condition, I assume these two, this one, and this one, and then nu, lambda, kappa, mu are the system parameter, and this additional parameter, epsilon 1. This is a given number. It's just for the technical reason. I assume that this should be in the 1 quarter and 1, between 1 quarter and 1. Okay. So if roughly speaking, our result for the sufficient condition is this. So if this condition is satisfied, this condition is satisfied, then we have a bimodal distribution. This is our result. This one. I go into some discussion about the biological implication for this condition. So I rescale this parameter. So this the NUNA is the protein degradation rate, this one. So I scale every parameter by this protein degradation rate NUNA. Then the sufficient condition, necessary condition, will become this and this one. So from these two conditions, this scale condition, I have some implication. So first one is this one, the high protein production rate. So high protein production rate. So again, this is mu delta. Mu delta is related to the transcription rate for the protein. I skip this the transcription process. So the new mu hat is mu delta is a transcription process. So this one say that this transcription rate should be sufficiently large to have a bimodal distribution. The intuition is very clear. If this small this transcription rate is small, it means that you cannot have the system will not accumulate enough the protein to support bimodal distribution. So this guy should be a very large to support bimodal distribution. If it's very small, then you can expect you can expect a monotone decreasing distribution. Nothing will happen because now the protein is produced. And the second one, this one, kappa delta. Kappa delta, remember kappa delta is describe the transition rate from the on state to off state. So if kappa delta is large, it means kappa delta is large, it means that the gene is more likely to be in the off state or in inactive state, off state. So the gene will be shut down. So if kappa delta is very large, so it means that gene is more likely to be a shut down. So you will expect the monotone decreasing state distribution. So this should be small. And how small is proportional to the proportion to this the 1 over the transcription rate, 1 over U delta, this one. The second one is also clear. What's the lambda delta? Lambda delta is described is this activation function. This activation. So recall that this activation function, we have in our model we have a dimer protein or dimmerization process. So the dimer will interact with the DNA and DNA through this inactivation function. So this lambda delta stands for the dimerization process, the strength of dimerization process. So if this is large, it means that the dimer will push more the DNA or gene to be in the on state. So you are more likely to have, you will open the promoter, then you will have more protein produced. So this strength, the dimerization process, this strength, this lambda delta should be small. If you are too large, then the gene is more likely to be on state, then the more protein is produced. So it means that many protein are produced. So there will be no state which are associated with a small number of proteins. So you will eventually you will have only a unimodal distribution, one peak in the protein number. So this number small means that the gene is more likely in the unactive state, and lambda delta small means that the gene is more likely in the off state. So it somehow is in a balance state. So this is considered with the well-known so-called well-known principle that if you would like to have a bimodality in the system, then the promoter activity should be slow. So we have two numbers. This involved in the transition from the on state to the off state. This lambda delta is involved in the reaction from the off state to on state. So these two numbers should be small to have bimodality. And the final is also not clear but also interesting, because this is Gina is describe the base of activation. So this activation function consider two parts. This part is contributed by the dimer, and this part is just a basal activation rate. This one. So you should be in the order 1 size. or one side. Again, if you have too large size, then you will not get a bimodality. This one. So this is this is our by implication for our result. This one. So if we go to assume that if the level of gene or protein are sufficiently large, then we can reduce. We can have we can use only the ODE or deterministic system to describe this network, and the equation equation are given by this three component ODE. This because it's ODE and it's very easy to solve. Not easy because we have a nonlinear term here. This zero nonlinear term here, but anyway, we can solve this state. And then we can see now if we have this relation, then we have this relation, then we can have a unique positive state for the ODE. And so if we have this condition with this sufficient condition, then we will get a bimodal distribution, but their corresponding deterministic ODE have only one positive state. So it means that in this case, if this condition 9 and condition 9 and condition 13 hold, so we'll have a noise-induced bimodality. And because I have the time is up, so I will briefly discuss the idea of our method. So basically how do we, because the number of chemical method equation, the number of equations in the chemical method equation is infinity. So it's very difficult to just solve this equation. So our approach is first to truncate this chemical method equation. Truncate. So we have a finite number of equations, but with we also have used the probability bounding condition because we truncate this into a finite system. And just do some manipulation, and we can divide these two equations, and also you need to derive some a prior bound for this or for the solution of this truncate system. So I need to carefully derive some a prior bound for this solution of truncate system, and then we can derive these two equations. This one. So this Rn is a ratio. It's a ratio. This one is the probability for observing N protein, and the gene is in the on state. This is in a denominator is in the off state. So this quantity describes the promoter activity ratio. So if this large, means that the gene is more likely to be in on state. On the other hand, this one is small, then it means that the gene is more likely to be in off state. And this equation is quite nice because you can see that this the promoter activity ratio corresponding to the n protein number equal to n. This is corresponding to the protein number equal to the n plus 1. This is a constant. This is a constant. Beta 9 is a constant. This is a constant. This one constant. This function or this function Pn is also a constant. This is a constant. This n is a protein number, and this activation function, knowing function. So this this equation, the equation 14 fully, how can I say, fully determine the evolution of a gene of the promoter adaptivity. I can determine the promoter adaptivity ratio only use this equation. Very nice. You don't need to solve this chemical master equation. And this one, the equation 16 is nice because this one, this is the probability of observing N14. This the denominator is the probability of observing the N+1 14. So if this ratio is larger than 1, this ratio larger than 1, it means that you will somehow locally you will have a decreasing distribution locally. And if it is larger than 1, so you expand that locally, you will have an increasing distribution. So I say that this number, the model detection ratio, because you will tell us that this distribution will be going up or going down, depending on it's a small, is this quantity is small, is less than 1 or larger than 1. And the governing equation is also nice. You see this one, and this constant is a protein number. So and this is the protein adaptivity ratio. So it's also consider our institution. The gene adaptivity fully determine the shape of the steady-state distribution. This one.
Sorry, Professor Tsai. Due to we are a little bit over time, you conclude in 2 minutes.
Okay.
Yeah.
Okay. Sorry.
Thank you very much.
Okay. So these two equations. Then, so if you have these two equations, so you just you need to solve these two equations. But basically, this is the back wall. It's a backward because n plus 1, so you have some backward recurrence relation. This one. So then you somehow you need to find a very end or very end, then find a very end and then integrate to get what will happen for this the whole network system. So finally, I would like to say that we also have this one, and then this is shown that if n is larger than this ratio, then for any steady-state distribution, if n is larger than this one, then you will get a monotone decreasing. This part. So n larger than this one, then the distribution always the monotone decreasing. So we only, if we would like to study this distribution, is the shape of distribution, we only focus on this side, between the 0 and this number. So basically, we use these two equations, and we also focus on this interval, and then we determine in which condition we can have this one and this one, and then we get a bimodal distribution. So I think thank you very much. I end my talk here. Thank you very much.